Hi, and welcome to Module 6. Today we are going to go over two chapters, two concepts, Chapter 27, Risk Assessment, and Chapter 28, Communicating Environmental Health. So first, Chapter 27, Risk Assessment. So what is risk? Risk is the probability that some adverse event will occur. And there's risk in almost everything that we do in our lives. There's risk in driving a car, there's risk in going swimming. When we talk about environmental health risk assessment, we're usually trying to evaluate the risk to a specific chemical agent or a specific biological agent. And the risk assessment process can be very, very complex. There are complete master's and PhD programs on the science of risk assessment. So the goal for the students in this class is to have a fundamental understanding of what goes into a risk assessment, so that when you're presented with the outcome of a risk assessment in whatever field you're in, you'll have an understanding of how that assessment was done. So the risk assessment is a stepwise process of organizing information on a hazard, such as a chemical hazard. And the ultimate goal is to inform the decision makers, the people who are making decisions about what to do with a contaminated piece of land or whether or not someone should enter their house after a chemical spill. The goal is to prevent populations from being at risk of adverse health effects. And these are mathematical equations that are done to estimate risk, again, that can get very complex. It's a very new science, so risk assessment was established formally in 1983 by the National Academy of Sciences. The guiding principles are found in the Red Book, which is thousands of pages. It's updated fairly frequently, but it's the guiding protocol for risk assessment in environmental health. So we're going to go through the 5 steps of risk assessment, again, so you have an understanding of how the risk assessment process works. The first step is problem formulation. This is a step where you involve all of the stakeholders. You all get together, anyone who has an interest in the outcome, and you set your goals, you design your requirements, you talk about the concepts, you talk about the exposure pathways. Is this exposure from people who are riding their bike on a bike path? Are they exposed to contaminants in dust? Is this exposure at a daycare setting where you're worried about young infants? So you go through all of the thought process of what exactly you're assessing. And this really helps to make sure that all the stakeholders are involved from the beginning so that they're more likely to cooperate with the outcome. Step 2 is the hazard identification. This is where you really ask, what are the health effects from this hazard? If it's a chemical, you want to look at all the toxicology information and all the epidemiology information. The epidemiology is very important to support whatever health effects you've seen from the toxicology from the animal studies. And you usually do a weight of evidence analysis, which means that you look at all the available science and you determine that most of it supports a certain outcome or a certain hazard. Step 3 is the dose response assessment. And this goes back to some of our discussions back in Chapter 6 about dose response in the toxicology lecture. Dose response is the relationship between the dose of the chemical and the adverse health effects. And this really is used to understand what this chemical can do in a human population, even though this is based on animal data for the most part. It's used to understand the risk to humans. And the shape of the dose response curve is particularly informative to people who are doing a risk assessment. So if you look at the top part of this graph, you see the dose response for a non-carcinogen. This is a chemical that could cause an adverse health effect like liver disease or kidney disease or developmental effects. You can see on the x-axis that there's a certain amount of chemical that can be tolerated before there's a biological response, and that's what's called the threshold. Below that threshold dose, you're not going to see any response in your animals, and you would extrapolate, you would not see any response in your humans. And then once that threshold level is reached, you see the curve start to go up, so the greater the dose, the more biological effect there is. On the bottom, you see a dose-response curve. You see 2 dose-response curves for carcinogens. Carcinogens are mostly assumed to work via a non-threshold mechanism. So even at the lowest doses on the x-axis, you see that every single bit of increased dose leads to an increased response. And that's because for carcinogens, every single exposure can impact your DNA and can influence the future cancer risk. So step 4 is the exposure assessment. This is where the scientist is trying to understand the chemical intake. So you want to know the exposure setting. Is it someone breathing air in their house? Is it someone who is swimming in a recreational spot in a lake and there's a chemical in the lake? You want to know the exposure pathway. So is it someone drinking water, breathing air, ingesting contaminated dust? There are very many exposure pathways, and this is where you characterize what's the exposure pathway. And you also want to think about who your population is. Are you looking at exposure to children, which are often the most sensitive? Are you looking at exposure to pregnant women? And then you calculate the intake of the chemical per body weight, because that's the way to normalize a dose. Regardless of how much a person weighs, a dose can be normalized in that way. The last step is step 5. That's risk characterization. This is where you put all of your equations, all of your inputs into a mathematical model, and you determine what level of risk is acceptable. For carcinogens, many scientists believe that a 1 in a million lifetime cancer risk is considered de minimis. So if exposure to a chemical in a certain setting increases your risk of getting cancer by more than 1 in a million chance, that's considered unacceptable to most scientists. For non-carcinogens, you look at a ratio. There's a ratio of the exposure dose to the dose at which there's no health effects observed. This goes back to your dose response information. And if that ratio is greater than 1, then it indicates that there could be a concern. And the risk is usually characterized sometimes for the average population, but it's more likely to be characterized for the 95th percentile. So if you're looking at exposure through drinking water, you want to characterize the risk for the people who drink the most water to make sure that you're protecting the entire population. So the next step after risk assessment is risk management. So risk management is a separate process from risk assessment. They're done by separate entities. Risk management is the process of identifying, evaluating, prioritizing, and choosing among policy options. Again, ever since the Red Book, the 1983, the step for risk assessment was established, risk management was recognized as a separate process. So an example of this could be that if a risk assessment determines that the amount of chemical in drinking water should be about 1 part per trillion in order to avoid adverse health effects, the risk management decision might be that 1 part per trillion costs too much money to remove from the public drinking water. The risk management decision might determine that 1 part per billion would be acceptable. So there can be a distinction between the risk assessment, which tells you what a health-based exposure level would be, and a risk management decision. Risk management has to include things like cost and feasibility. And this is also where the stakeholders can be very involved. So if you have a stakeholder for a chemical company or a chemical product that's very involved in the process, that person can really affect the risk management decisions. Okay, so now we're going to move on to communicating environmental health. Communication is very important. I'm sure all of you by this point in your lives realize it's very important to be a clear communicator, not only in environmental public health, but in every aspect of our careers. So in the United States, there's a movement towards providing information to people. This is done through several of the examples listed below. Through the workplace right to know information. If you're working with a hazardous chemical, you should be informed of that. Communities should be informed if hazardous waste is present in their community. People who drink public water have to be informed about what's in the water. But there's a difference between providing a lot of information to the public and communicating that information. So for example, if a public drinking water supplier provides an Excel sheet with 400 rows about chemical detections in their water, the average person cannot take that 400-row Excel sheet and drill it down to one specific take-home message. And that's what risk communication and environmental health communication is. It's taking a lot of scientific information that can be very complex and providing it into a single message that can be understood by the public. So there are a few guiding principles. It's really effective if you use simple and clear messages. It's important to be scientifically correct, but it's also important to recognize that if you use too much scientific information and if you get too complex in your message, it's not going to be understood. So in Vermont, we always target all of our messaging to a 6th grade readable level. So if someone in 6th grade can read and understand our messages, we think that we've done a good job communicating. It's also important to repeat your message. You can repeat the same message on phone calls with the public, on interviews with the radio, on TV interviews, on social marketing, on your Facebook page. It's important to use the same messages in multiple different ways. And one of the most important things in risk communication is that the person who's delivering the message is someone who's trusted. If someone is delivering a message and they're not trusted, the message, no matter how good it may be, is not going to be received well by the public. And in order to change someone's behavior, you want to make the new behavior easy, fun, and popular. So if we're trying to communicate the risk to arsenic in private drinking water, what we want people to do is to test their water. And that's changing a behavior. Most people do not test their water. So to make that happen, we would have to make that behavior easy. It would have to be, either free or available at a somewhere that's very easy for people to test or very affordable. It would have to be fun, and it would have to be popular. We would have to make that behavior something that's seen as what everyone does. So then if you're not doing it, there would be this peer pressure or social pressure to conform and do the activity that everyone is doing. So again, the objectives of risk communication are to inform people and to build or repair trust and encourage appropriate action. And there's a whole science, like a behavioral science almost, of risk perception. So this means that people might not have an appropriate response to a risk. So people's response to a risk might not match what the actual risk is. So for example, you might have a person who has never tested their home for radon in air. So radon is a very serious health risk. It is naturally present in our environment, but is one of the leading causes of lung cancer. It can be remediated from your house as long as you test it. But you might have someone who's very concerned about the health effects from GMO foods. However, they've never tested their home for radon. So there's a big difference in how people perceive risk. And there are a few different models that talk about this. The example I just gave is the risk perception model. There's also a mental noise model. When people are stressed, they can't take in a lot of information. There's a negative dominance model, which means that people listen to the negative information more than the positive information. And there's also the trust determination model. That goes back to the conversation about having a trusted messenger. No matter how good the message is, if it's delivered by someone who's not trustworthy, it's not going to get through to the public. So there are 7 cardinal rules that EPA has provided for risk communication. The first is that the public has a right to participate. It's important to tailor your strategies to your audience. If you're speaking to a community of parents about exposure in a daycare setting, you want to keep in mind the questions they might have, that are specific to children. Whereas if you're presenting information to a group of workers in the steel industry, you want to know what their specific questions might be ahead of time. You have to listen to your audience and understand what other factors they're dealing with other than trying to, understand the scientific information. Be honest and transparent. Use trusted sources and trusted voices. And this goes back to the trust issue. You have to plan for media influence. Media always wants to find a juicy story, so there'll always be some sort of twist that they put on whatever they publish. And then again, speak clearly. It's important to show empathy, avoid technical language and jargon, because the complex scientific messages won't get you very far. And just to wrap up, that there are so many challenges in effective risk communication. It's critical that you have a spokesperson who understands how to communicate very well to the public. It's good to have a communication plan. That plan can often address some of these psychological barriers or cultural factors that lead to risk misperception. Okay, thank you very much.